It looks like it's time to get our final talk. So my name's John Tully, and I have the pleasure to introduce our fourth speaker, Bob Grubbs. As Laura observed in her talk, all of the speakers today, for all of the speakers, catalysis is a major part of their research, and that's certainly true for Bob. Bob has been involved in designing and applying, synthesizing complexes that catalyze basic fundamental organic reactions, and in particular olefin metathesis reactions. And in fact, his ruthenium-based catalysts that he's discovered and applied are now extremely widely used and bear his name. Bob is the Victor and Elizabeth Atkins Professor of Chemistry at Caltech. He was awarded a Dreyfus Teacher Scholar Award in 1974. Since then, he's won a number of lesser awards that I won't bother to list. So it's a pleasure to welcome Bob, who's going to talk about the design and synthesis of catalysts for use in organic polymer synthesis.
Thanks. Oh, I can't see the city. I closed the lights, closed the windows. Anyway, so it's good to be here, to be part of this symposium. It was pointed out I received a Dreyfus in 1974, before most of you were born, many of you. And I knew it was a long time ago when I called Mark and asked, because I couldn't find anything about it in my files. But my assistant's on vacation, so I can't find anything else anyway. And so I called Mark and asked if he could find at least the title of this thing. Turns out there's not real titles for Dreyfus awards. And so he immediately sent back and said, it may be difficult because it's archived. You know you're getting old when you've been archived. Fortunately, they found it. And it was really fun. So he sent me the nomination, which was, I wish I'd known my chairman thought that much of me at the time. When he wrote it, I think he was doing it. But it was interesting to see what I was working on then. So I started out on 3 projects. I'm not sure that's the wisest thing to do when you're getting started. But there were 3 pretty different ones. Polymer attached catalyst, which we worked on for a long time. The mechanism of, at the time, metathesis was the key one of that, and then metal stabilized stuff. And we ended up publishing papers on all 3 of those. I'm not sure we made major contributions to any of them at the time, but anyway, chairs put those things in. But the other one, which was interesting, was talking about the olefin metathesis reaction. And at the time, I wasn't totally sure of this, but anyway, it says new catalysts and new uses may result from a better understanding of this catalyst. So that's what we've been spending a long time doing. So about 36 years later, we're still doing that. And the other part of it, too, associated with the Dreyfus thing was, it was really one of the first grants I got for the people who are just getting started. I think I wrote 9 grants before I got one funded. I didn't know any better, so I just kept writing them. And so basically, this was right after that and allowed us to actually do some of this stuff. And so at that stage, we had one idea about the mechanism of metathesis. By the next year, we had come up with another idea and had done the experiments. And this was really the paper that changed sort of the direction of my career, probably, which is this one where we finally showed a mechanism and supported a mechanism for metathesis, which was sort of known at the time. And so metathesis is this reaction which people know about now, but I found out about it first in 1968, 69, when I was a postdoc. And it just fascinated me that here was a catalyst that would make and break carbon-carbon double bonds and put them back together very fast, very efficient. But we had no clue what the mechanism was. We had no clue what the catalyst was. The catalyst came from mixing a bunch of stuff together. It was tungsten hexachloride, it was alkyl aluminums, it was this, it was that. And you didn't even know whether it was a heterogeneous or homogeneous catalyst, because you would centrifuge a tube, and half the time the liquid part worked, and the other time the solid would work. And the other problem is that it took graduate students a while to get to do it. So some graduate students couldn't get it to work because they were too careful, and others couldn't get it because they were too sloppy. You had to get just the right amount of air in. So it was a disaster. Now, the person who proposed this mechanism was named Yves Chauvin, and Chauvin published this in the early 70s, and it wasn't until 74, 75 when people started recognizing it, and he had two strikes against him. Is that one, he published it in a polymer journal, and chemists didn't read polymer journals then, and the other thing was he published it in French. And so the combination of those two, it was ignored for a very long time. And so the question was, how did this reaction go? And so trying to distinguish this from our original idea, lots of other people's original ideas, resulted, in people. All the experiments were consistent with this, with this metal carbon double bonded species. So our group did a lot of deuterium labeling studies. Tom Katz at Columbia did a lot of deuterium labeling, and these all put together ended up with a pretty consistent picture of this catalyst involving the chemistry of metal carbon double bonds. There were only a very few metal carbon double bonded species known at the time, and those really didn't do the right kind of chemistry. So this was a pretty outrageous talk. So this is for the people who are not chemists and people who think about teaching. And so then how do you show this reaction? This looks pretty dry. Metal carbon double bond, carbon double bonds, making rings and stuff. It took us about 10 years to get this all sorted out, but it's really easy. You can show it with a dance. It was square dancing. I grew up in Kentucky doing square dancing. I'm not sure why it took me so long. So these are double bonds. There's metalecycle. Here's a double bond holding hands. Okay, and so this goes around, and so we start out with everybody being red together and blue together. But you see, we're about to get an exchange there, and then we'll end up with red and blues. So that's sort of the game of how this all works. And if this works, maybe. Oh, sorry. I forgot to turn off the sound. Can anybody recognize what language this is? There's a lady in black. That's the transition metal, double bonded to a carbon. There was a transition state. A metalecycle now cleaved. Okay, around we go. Here comes another transition state. Zap. There we go. Four-membered ring. Then they split again. So it's easy, okay? So that's how the reaction goes. I didn't think about it this way, except the Nobel Committee got really excited about this as being a molecular dance, and they actually did one on stage. So, and now being a really good catalyst, see the brown and the black get back together again, all double bonded and everything is good. And so the language was Hungarian. The video was made by István Horváth in Budapest. Then he's now in Hong Kong, but it's an easy way to show reactions. It's I use it a lot when I'm talking to high school groups. There's always the most popular girl in the school sitting on the front row, and some guy who's not, and so I get him to get up and do the dance. It's always worked really well. How do you pick? It's easy. And so basically the whole key then was getting a catalyst that worked. And so we started a long time ago, and Katz did some tungsten things, and then we did Fred Tebbe, who's a DuPont, did some really interesting stuff on titanium. We followed up on that. That's what got us into polymers. Dick Schrock made made these tungsten and moly catalysts that have been really effective, and there's lots and lots of great chemistry they're doing with those. Then we ended up over at ruthenium for a long, funny reason, and Bruce Novak got us into ruthenium, and then Sunbin Wen, who's now at Northwestern, made our first well-defined catalyst. And then we've been changing ligands ever since, making all kinds of complexes. And the nice thing about ruthenium is that olefins react in the presence of almost everything else, so it opens them up for doing lots of chemistry. And so once you have a catalyst, you can use them lots of places, and so you can do cross metathesis. Laura showed one of those. You can do ring closing. That's where most synthetic chemists know about it, is making big rings. It's been used in pharma in lots of places. You can make polymers, and that was discussed earlier, and we'll talk a lot about that today, and you can make polymers by that. So basically, any place you have carbon-carbon double bonds, you can do something with metathesis. And so we've been designing catalysts. I mean, this is a fun thing to do. Once you get in the game, it gives you a lot of excuses, and you can find lots and lots of applications. And so there's the basic reactivity, and then you can tune it by tuning the ligands. And there's now probably at least 500 or more different catalysts that people have made for doing metathesis, but they all fall in the same thing, the same structure that Sunbin made long ago, which is ruthenium, 2 halogens, almost always chlorines, 2 neutral ligands, phosphines and heterocyclic carbines, oxygens, and a metal carbon double bond. And they all react by about the same mechanism. And so everybody has their own favorite catalyst, which they name after themselves. It's a game. So these are just ones we made in our lab. So that was our first one. This was fast initiating. I'll talk about that later. You can do it in water. You can make it chiral. You can make it really stable. And so Amir made a real contribution. He introduced this ligand system, which has been very effective in making very stable, very active catalysts, and get rid of the phosphine. Turns out phosphines can be bad in some cases. You can put them on supports. You can make them all kinds of stuff. Dick and Amira have made an EZ selective moly catalyst. We're making some real progress now with ruthenium, finally, after about 10 years. And the other nice thing about this is it's easy to make. And if people are going to use it, you got to have it available. So this is a barrel of 100 kilograms of metathesis catalyst. And so there's a catalyst right there. And it's easy to handle. This is in Pasadena, which some people claim has some of the most oxidizing air around. And so actually 5 barrels of this was shipped off a couple of months ago. And if you've ever bought this catalyst from Aldridge, it's sort of scary how much you could sell that for if you could sell it to anybody. Anyway, but you can't obviously sell it for Aldridge prices. And this is going into making polymers and lots of stuff. So it's easy to handle, it's easy to make. And so then the question is, what are you going to do with it? And I'll just show one sort of application, which is just developing, just to show where, starting with a catalyst system, which, 19 and whatever, we were interested in just because the mechanism seemed to be really unusual, and we had no way of thinking about it. And after, spending my time with the Breslow group, where mechanisms was key, that was really a fun problem. In fact, I thought we were going to work on this, and I was just hoping to get me tenure. That was really my major goal in life. So I didn't have to go back to Kentucky and do whatever I had to do there. So where we've come from there to now is we've got this catalyst that works. You can make it on a big scale. And what can you do with it? Well, one of the interesting applications came out of a collaboration between DOE and Cargill, because DOE wants to use renewables. This is part of the whole green chemistry thing. And Cargill's interested because they have unsaturated oils, vegetable oils. What you put on your salad is an olefin. So and so we can do chemistry on those. Now that we can tolerate functionality. Okay. I've just got a phone. Okay. Anyway, so all these modern devices, and so you got that, and so it turns out that then using catalysts and so Materials, this little company that's making all this stuff, and our group working together, this has worked out pretty well. So then there was a spinoff between Materia and Cargill, a company called Elevance, which is sort of cruising along, making all kinds of interesting things like waxes for candles, and that didn't seem to be too exciting. I just found out there's a product now being sold by Victoria's Secret where they're modifying a seed oil and using it in makeup because it can then be vegan. It's great. I didn't think I'd ever get to Victoria's Secret. But here's the exciting one. And so Elevance has just announced this thing, which will, it looks like it's going to happen. And so there's a joint venture with a company called Vilmar, and they're talking about making 400 million pounds of stuff a year using metathesis and stuff. And so the basic idea is to have a refinery where you start with seed oil instead of a barrel of oil, and you do a little pretreatment. Our catalyst doesn't tolerate everything. And then you do metathesis, putting in ruthenium catalyst, and you can put in lots of other goodies here. You then break it up into many pieces. You can distill. And so part of the pieces will be esters, and so those go down and make a lot of things. The other part will be hydrocarbons, and so those can go off and be hydrogenated and make fuels. And so that's the plan and the proposal. We'll see how well this all works, but the idea that someone's putting a whole lot of money in to build a plant to do this is going to be interesting to see how it goes. So that's the reason that we need to make hundreds of kilos of catalyst. So that's one side of things. And so the other side is we got these new catalysts. So what can we do with them? So you can do organic synthesis. We've done lots and lots of that. And other people do that much better than we do. And so this whole idea of making materials. And someone said earlier today, we've gotten to the point now where you can draw a structure and you can go in the lab and make it. And so I think we're getting to the point where we can now start to really design stuff, and especially in polymer chemistry. And also the other thing is that there were some real lessons from physical organic chemistry, which is where I started. And so in physical organic chemistry, there was lots of synthesis done, but one was trying to make a special molecule that would tell you something about structure and reactivity. And you know, I basically did my thesis on a reaction that gave a 7% yield. We didn't care. We got the compound we needed, and we could go forward with it. So sort of that old idea, rather than sort of thinking about making something really complex or useful, can we design molecules we can learn something from? So that's one area of polymer chemistry that people haven't done. So this sort of challenge, can we make anything? And so we're worrying about block polymers and cyclic polymers, and this introduces a whole new set of ways of synthesizing, characterizing, and purifying. Some of this stuff is working on for quite a while. Some others reasonably new. And so why is metathesis good? There's lots of other new things now that's come along. And so metathesis allows you to make polymers because, first of all, you start with a well-defined species. We know from a lot of mechanistic work that you start with a 16-electron species, you lose a ligand, makes a 14-electron species. That's what turns over. Termination is slow. These things are slow. That's the propagating species. And so to get control of the molecular weight, we need to be able to get the initiation and propagation rates all balanced out properly. So since we've got a system we know a lot about, we can then go do things. So it turns out that these second-generation catalysts, whatever generation you want to think about them, anyway, these with N-heterocyclic carbenes were really reactive. And the other thing they did for us for norbornenes, which remember, if you're going to do a living system, you can't have chain transfer. And so the nice thing about norbornene, it's a lot of ring strain. And then also the double bond you make has highly hindered things on both sides. And so it doesn't like to go back and backbite. So it's easy to keep down chain transfer in these. And so the other deal is when you make those by Diels-Alder, when you make norbornenes by Diels-Alder, you get a lot of endo. And it turns out that the first catalyst wouldn't polymerize endos very well. Turns out these do. But they end up giving you really broad molecular weights. We had to get molecular weight distributions of over 2, which is not good at all. And it was because initiation was poor and just weren't under control. But we found that by replacing the phosphines with pyridines, these things would initiate really fast, and you can make really well-controlled structures. So that's already a few years ago. So how does this work? Basically, a pyridine, first one comes off easy, the second one comes off fast, makes the 14-electron species. You add norbornene, metallocycle, boom, 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 keeps doing it. When you run out of monomers, pyridine can go back on, or one of these groups to stabilize it. And then you add ethyl vinyl ether, or vinyl acetate. That then cleaves the double bond, puts a methylene at the end, and puts that on the ruthenium, which is much less reactive, and so it's easy to stop things. And so using this, one can think about a lot of different things to make. And I think we basically looked at all of these. Sometimes we make these without trying, but all of these we've tried to do. And today I'll talk about stuff we're doing now on graft brush and on cyclics. Cyclics we've been working on for a long time. There was a poster outside about cycles, and so I hope you had a chance to look at that one. Our method is a little different. So brushes. Obvious why they call them brushes. And so it's essentially a long backbone with little polymers hanging off the side. So these can be reasonably high. These are usually a few thousand molecular weight, and those go along there. And people have been making these for a long time. And they've been hard to make controlled because the problem is what you want to do is build up steric bulk along the backbone as these things grow because you want to be able to force this chain to straighten out. But you can imagine what happens if you've got a reactive group right there, that it's going to get shielded by these groups, bringing in another monomer. You build up steric interactions already. And so if that's not super stable, it will die and do other stuff. And so it's been difficult getting really good control of molecular weights as well as the as high efficiency. So the question is what about these? We've got a good way to control things. We've got 25 kilocalories per mole built into driving force, and we're also putting things 5 carbons apart rather than 2 as you do in most polymerization mechanisms. So that gives us a little more space to work. And then the other part of this, again, if you were going to make polymers about 10 years ago, you had a few ways of doing it, control. Now with ATRP and all these living radical things, one can start to construct molecules really, really easily and with good control. And so it's easy now to crank stuff out, and so I should put our ATRP in, but atom transfer radical polymerization. But basically what you do is you start with an alpha halo ester in this case. You put in copper in your monomer under the right conditions, and basically the halogen comes off, makes a radical, you add things, it goes on and off, and at the end you end up with a bromine. And you can control the molecular weight by controlling ratios, etc. So you can make a whole bunch of stuff. Styrenes, high TGs, low TGs, the whole range. And then the other part of this, we can use the other sort of hot new reaction, is we can take that bromide, which is there, treat it with sodium azide, and so we can make a ZIZ at the end of all of these. And then we've got our other modular part, which is the acetylene, and then we do a click reaction, and then we can tack anything we want. So we're going to do ATRP click and rump. I mean, how trendy can you get? Okay? And get you to that product. Also, the other thing we can do is the bottom is to do polylactide. And again, there's lots of good catalysts, and so this is easy to control, and you can make these very narrow polydispersity with really good control of N. So monomers are easy to make. Good control. PDIs, you want to get to 1, pretty close. So this is norbornene, polystyrene, and that's the molecular weight of the side chain. And then you can make polymers, and so here's the monomers, here's the polymers. First thing is high conversions, which has been a problem in the past. Polydispersities, really narrow, narrower than I usually like to trust. And we can control molecular weights of side chains and backbone. And the polydispersity, this is for the polymer guys, is that you buy standards, polystyrene standards, to calibrate your column, and that's been black. And the red ones are our compounds we made, and they're narrower than the standards you buy. So these are well controlled and really well put together. So next thing is, what do these things look like? And is there any interesting stuff you can do with them? And so this looks like worms. Used to fish a lot in Kentucky, and so I got to know how to thread those on a hook. And so there's a polymer, okay? And you see it's got a really it's for a polymer of that length, it's 140 nanometers. It's pretty rigid, and so this idea of putting these backbones on, making the backbone stretch out, is a pretty good idea. These sort of set down on the surface based on the sizes of these things. And the other feature is that if you measure the length, so one of these is 150 nanometers, based on and the degree of polymerization of those was 224, which we measure by GC. This we measure by measuring that, and so you divide those out, and it turns out that each carbon-carbon bond is about 0.25 nanometers, which means it's stretched and trans. So it's really stretching out these backbones and pushing them in the directions, and so that was published a little while ago. And this is collaboration with the Cornfield group. The key guy is Jan, who was a phenomenal graduate student who unfortunately just graduated. It tends to happen with good graduate students. I sometimes wish I could become a biologist. So anyway, So the next question is, can we make blocks out of these? And so what's going to happen with these is that if you're not a polymer chemist, one of the keys in polymer chemistry is polymers hate each other. They hate to mix. And so if you then take two polymers, moderate molecular weight, and you put them on and you force them to interact, what's going to happen? Okay? So this is a standard block of polymers. So they're separated. Here we get them mixed together, random. And we choose backbones, and we measured all of this so we can get, at least in some cases, random polymers, because you can watch the monomers disappear at the same rate. Okay? So how are these things going to take care of themselves? How are they going to assemble? Well, the first thing is if you start with a random brush, and so from the AFM picture, we've got something like this, long, fat rod thing. Okay. And so then how are these random polymers going to interact? Well, if you look at this using Sachs, it turns out that the lower molecular weight ones form a fairly ordered structure. And the spacing of that ordered structure is about 14 nanometers. So one model, and there could be many models, but the one model that fits is that basically the chains start to phase separate along the backbones and start to stack up by interdigitating. That's one model. As they get bigger, things start to get lumpier, and you make them unsymmetrical, things really get lumpy. So we're still trying to sort some of this out. These are not as ordered as some we'll see later on. That's one model. It could be there. And so we ship some of these off to Tom Russell. He's looked at them. In really, really thin films, they don't appear to form these stack structures. They tend to just sort of spread out on the surface. And so we've got to go back and get this stuff sorted out. But when you make the blocky ones, now the interesting stuff happens. So now we do the Sachs. So this is 100-100. And, this is really a well-ordered structure. And if you look at the spacing, it turns out it's about 116 nanometers, which is about the length of the chain, of the backbone chain. If you cut it in half, the spacing goes down. Spacing is about 50 nanometers. So the best model for this is having a fully extended, almost fully extended backbone, and having these things interdigitating and stacking up. So you end up with layers of that. And so you see this gives us a spacing and an order of over 100 nanometers, whereas the other systems were in the tens of nanometers. Okay. And so then the next question is, can we make them bigger and they still work? The problem is that when you make them bigger than this, you see we've already lost our primary over here, so you have to go to USACs, I'm told, and we don't know how to do that yet. And so, but you don't have to, because there's an easier way. So if you make a 200-200, and you look at this with light coming through it, it's yellow. But if you look at reflected light, it's green. Okay? So this fits the category of what's called a photonic crystal. And a photonic crystal is an interesting material, and it takes spacing of about 170 nanometers to give you green, which is sort of fit. And why is this important? Well, it's a lot of places. It turns out butterflies' wings are the color they are not because of dyes or pigments, or because of these photonic crystals, these space-ordered things. In fact, lots and lots of insects do that. So it's pretty interesting. So you think about it, you got a spacing with different refractive indices, and the wavelength that's reflected is just associated with the size and difference in the refractive indices. So this one is about 170 nanometers based on that. Probably not super accurate, but anyway, there you go. So these things make these things pretty well. And so again, Tom Russell's looked at these, and these now actually making thin films. And so these films are 41 nanometers, and the spacing is 62. So this turns out that the spacing is greater than the thickness. And so these actually set down on the surface. I'll show you some more about that in a moment. And this is a material that's made from PLA. And so PLA is polylactic acid, and it's easy to hydrolyze. You can buy drink cups now that are made out of polylactic acid and stuff. So that's easy to go. And so the other block was polystyrene. And so if you put these down and solvent anneal them, you end up making an ordered structure, which appears to be alternating polystyrene and polylactic acid, and they've got a variety of other things to demonstrate that. Then if you treat this with base, it retains the ordering, but it becomes a bigger contrast because now we think we're taking out the polylactic acid, and so now we've got polystyrene alternating with spaces, which is just air. So I think there could be a lot of things, and this is the magic thing down here. I used to think it was hokey, but I'm liking it as I see it more and more. And so this was taken by a cell phone. And so that's basically a solution of this polymer and just evaporating the solvent. And you notice what happens is you look at it, it's colored. So basically, it's spontaneously forming these really well-separated phases just by evaporating solvents. You can anneal them slightly and make them better, but you don't really have to. And you can also tune the colors by tuning the sizes. And so this is the brush, and then this is our big random coil, and so we can go different colors. Again, these are all just evaporated, so they spontaneously assemble. So the way to think about these is that you basically have all these rods, and they have different colored ends, and so the colors get lined up and make these structures. And since it's not coiled, if you have coiled polymers and you try to get phase separations, they sometimes take a long time because you got to get things untangled and all worked out. This is you're stacking sticks that work pretty well. So these brush polymers give you the extended backbone, which is what people have shown before and what we anticipated. Based on some work that Greg McKenna's doing on these, is that there appears to be very little entanglement of the side chains with each other. But you still get self-assembly driven by phase separation like you get in normal things. But the deal is that these are really big molecules, and they spontaneously assemble just like crystallization rates, like small molecules, but you get length scales of polymers. And so we can spontaneously form assemblies, have length scales of 100 nanometers or more, doing it very rapidly, just like you can with small molecules. So we'll see where this goes, see what's happening. This is still pretty new. We want to do there's lots of things to do with this by changing. Oh no, once this thing starts, it doesn't want to quit. I keep forgetting I go back to this. But basically, what we want to do is make these things, we're putting cross-linking groups here so we can stabilize the structures and putting all kinds of different stuff in. So I think this is going to be something to keep us busy for a long time. Okay? So another area that's of interest is in the making cycles. And so if you saw the poster, you can see part of the reason. And the thing that attracted me to this was the early days I started going to polymer lectures. I point out, to some people that I've never had a polymer course in my life, so I had to learn it all on my own, which is good. And so I went to early polymer lectures, and reptation theory I was really fascinated by, and how polymer chains move. If you don't know polymer chemistry, it's easy. You know, if you have two polymer chains, they can't move this way. They got to move this way. And so it's got to move like snakes. So that's called reptation theory. So really early on, the question was, what happens if you have cycles? They don't have a head. There's lots of jokes about that, but we won't go into those. And so how are they going to move, and how are they going to bend? And so the question is, how do you make big ones? So most of the ones that have been made up to this stage have been in the thousands of molecular weights. And they're made, as we saw out there, where you can make really precise structures by making a long chain, have sticky ends, and get them to cyclize. And we saw really, really high molecular weights. I mean, really high yields. The question is, how are you going to make things in the hundreds of thousands? Because then it's going to be really, really difficult to get ends to stick together, and you got a lot of problems. And so Chris Pawlowski took this on toward the end and using metathesis of these cyclic catalysts. And so you have no ends here, you have no ends there. So in principle, you shouldn't get any ends in your polymer. But we know how that is. It's easy to draw structures and do chem draw characterization, but going in and really doing it. And so AJ made lots of new catalysts. So we could look at all of the different effects of the different parameters in my system is going. So the problem is that if this is fast, everything's dying at once. If this is fast and you make huge molecular weights, if this doesn't bite out, So it's got to bite its tail to spit out this. Then you end up with metal left in your chain, and when you're working it up and oxidizes, you're going to end up with linears. There's lots of ways of making linears and et cetera. So we had the question then, we knew we had different things, we knew a lot of it was cyclic, but how did we know that it was, how much was linear, and how could we analyze this? And so this is an experiment we did some time ago, which turns out to be easy to start with. It's taken a long time to implement, but it's based on this observation. So we can make these linear polymers with ammoniums, put in 24 crown 8. This goes back to stuff that actually started when Marcus was in the group. We made our first sort of couple of things, and we've worked with Fraser Stoddard and all kinds of folks on this. And so this sort of is left over from that. So you take an ammonium, you take a crown, it goes on. You can follow these in small molecules and in large molecules by watching the signal next door. In this case, going from 3 to 3,2. It's a really easy handle. Something fell. Oh, that's my phone. That damn phone. Oh, it's ringing. No wonder it jumped off. It's my son calling. Anyway, you should. No, it's okay. You shouldn't leave it on vibrate. It's okay. It's fine. So anyway, so you end up getting that, and if you do this, this amazed me. This is one for the polymer chemists in the group. So up to 100,000 molecular weight, we mix a lot of this in, and within 10 minutes, that signal is all moved up to 3,2. So on a really fast time scale, these things are threading onto the polymer. And we've done dozy, all kinds of crazy experiments to show that these things are all coupled. So it looks like it's pretty clean. So now the experiment's easy to be able to tell them apart. This is one that everybody can understand. Magicians have been doing this for 100 years or more. So you basically make a linear, and you make a cycle, and you make the ammoniums, and then you look at the NMR, and they both look exactly the same. Because the only difference between those two are ends. If you've got a polymer of 100,000 molecular weight, you don't have many ends, so you don't see them. You've got to look really, really hard to find them. So you can't tell them apart that way. But you can tell them apart when you put on 24 crown 8, is that, this one shifts a little bit left because you usually have a few cycles from metathesis. This one, no shift. Okay? So finally, after years of doing all kinds of instrument things and everything else and spending large amounts of money with Wyatt on light scattering and all kinds of devices, we finally have a chemical way, which is what I really like. No fudge factors. And it works, and you can screw this up. It's really easy to screw this reaction up if you use the wrong catalyst, if you use the wrong conditions. So here's some samples. This is mostly cyclic. That's a little linear. Here's a mixture, almost equal, and this one's almost all linear. So these are just running the reaction wrong. And then the other thing that AJ found was when he precipitated these is that when he looked at the product that came out, it was all cycle, and all the linear stayed in solution. Because the linear is being threaded, being shielded, and the cycle is not. So it falls out. So you can separate the two, and so that's how we're separating these things now. So we can make these. Another lesson I learned early on in polymer chemistry was I went to a lecture by Sir Sam Edwards, who helped develop the reptation theory and everything, and I was horrified as a chemist because Sir Sam drew this big squiggle on the blackboard, and he said, "I know there's atoms there, but I don't care." And so I worried about having a pretty weird polymer, but they don't care. So it's just the topology. So now we take this saying and we make hydrogenate and do things. And so now Greg McKenna is starting to look at this. Our initial results suggest that the slope is going to be different, and it sort of fits a model that people have had before. So hopefully we can solve this. But for me, it was like a nice synthetic challenge, and I hope we're there, and I hope we soon get this all taken care of so I can quit making cyclic polymers. Okay, so time to quit. Good show. Okay, so to keep people to think are Jan and AJ. Jan's now at Dow and AJ's at Washington, and Ben Borgsen, an Icelander, is taking over the brush project. And Chris is taking over the cycles, and we're adding on a bunch of other people to get this thing sorted out and finished. And thanks.
So we have time for
Yeah. Yep.
Can you control the PEI of the cycles?
Nope. So the PEI is 2 more or less.
Can you control the molecular weight?
Yeah, we can control the molecular weight, to a certain extent. It's partially controlled by the catalyst, and it's partially controlled by the concentration. Because basically it's a competition between growing the ring and biting off, and so you can control that a little bit by conditions. But it's sort of hard to do, and then you can also do it by letting it grow big, and then you throw in more catalyst, and so the cycles become substrates for the new system, and so you can slowly equilibrate it that way. But it's not as easy as we'd hoped. I mean, I had this great vision of basically having a system we could grow a big ring and then heat it up and have it snap off and make narrow polydispersity. We might pull that off someday, but right now it's not the case. Yep.
Bob, have you ever seen in bottle brush polymers any objects where the symmetry was broken? And what I'm getting at is, the stretching that you see of these things is caused by elastic energy.
Mm-hmm.
If you bend the bottle brush,
Yeah.
you can alleviate the stretching on one side. Of course, you make it worse on the other.
Right, yeah.
But what if you had a mixture of molecular weights, one that would tolerate stretching more or less?
Okay.
You might get, it'd probably be racemic mixtures, but
Yeah,
you get chiral structures. Do any of these things ever look like helices?
I wouldn't know how we...
Just like worms is really what I'm getting at.
Well, part of the problem is you have to do them on surfaces. And there's a lot of surface interaction, and so we have to be careful. I mean, where we're trying to get them to bend is we're trying to use these substrates to make cycles. And so we've made some humongous cycles. But also they tend to break apart. And so we can look at them, and you scan over, and you got a cycle, and you scan back later, and it's open. So, so the surface effects on these are pretty tremendous. And also, just trying to force them into a ring is doing what you're saying. It's really building up a lot of stress on one side. It's a long day.
Well, we have no more questions for Bob. Why don't we thank him and all of our speakers?
Thank you.